Would you mind maybe I'll just this week so that I can
I don't know when I'll get it written up. I'll get it written up before Monday. Yeah, 3 problems. Okay. All right, so the disappointing thing about today is that we're not going to get through everything I wanted to get through because in preparing these notes I realized I couldn't. So we'll pick a time to finish up. I do, though, independently of that, I would like to invite you all to our last particle physics class this Thursday at 5, where we'll be talking about the topic that we didn't get to in Physics X, which is grand unified theories and theories of everything and so forth. So that actually will naturally be the last topic in particle physics. So that could be our fiducial final Physics X meeting, depending on when we have a follow-up to this. Okay, so that's the bad news. The good news is that you're going to get to hear me call Zach a liar, and then you'll hear me apologize. Oh.
So, all right. So just to get started, we last time talked about 3 notions of entropy, some of which were more familiar to you than others. The first one, which I'll call A and refer to as A, is of course the thermodynamic entropy. And the thermodynamic entropy we recognize as that quantity S in the expression for the differential energy change associated with a change from one equilibrium to configuration to another under some reversible process. And then one of the important observations in thermodynamics is that S is non-decreasing. Okay, a second definition of entropy that we talked about is what I will call the statistical definition. And the statistical definition of entropy is that the entropy is minus or proportional to, there's some proportionality constant I won't worry about, probability, or it's a sum over probabilities times the natural log of the probabilities. And then this is just generically defined for a probability distribution. So some set of PIs, which are of course subject to the usual constraint that the sum over all of them is equal to 1. That's the statement. If you've got a set of probabilities, something's got to happen. So, and then the last notion of entropy is the quantum mechanical definition of the von Neumann entropy, which I'm going to say this a little bit different than I did last time, and then come back and refine the definition. Which is defined as minus the trace of rho log rho, where actually the rho in here, the rho is in truth any positive definite Hermitian operator. Okay, so you can actually extend the definition of von Neumann entropy to things beyond just the density matrix, but we know the density matrix is a context where that's particularly relevant. Yes?
Is it not derived from the above statistical?
No.
It's different.
It's different. So what I'm going to do now is connect these 3. Okay? These are very broad stroke definitions, but obviously they have some overlap. So, for example, if the probability distribution in B, so I'm looking at the statistical definition, is appropriate. So it's not just some random ass set of probabilities. But for example, if the probabilities are proportional to e to the minus beta times the energy of a state, so we've got some Maxwell-Boltzmann type distribution, then B reduces. Actually, it doesn't reduce, it reproduces A. Okay? So for certain probability distributions, i.e. like the probability distributions associated with thermal systems, the statistical definition reproduces the more basic, earlier known thermodynamic definition. And these statistical distributions, it kind of depends on what you're looking at. Typically we use a Maxwell-Boltzmann distribution, but you could also work in the macrocanonical ensemble and use the probabilities as just 1 over the number of microstates. You could also look at special cases like the Fermi-Dirac distribution, the Bose-Einstein distribution. But generally speaking, there are several possibilities. But for any given set of distributions, of particular distributions, you go back to describing the ordinary thermodynamics of a macroscopic system. And in particular, you reproduce these differential relationships between extensive quantities. Okay, another connection is that if rho in definition C is a diagonalized density matrix. So last time we actually introduced what a density matrix was, but just to remind you, a diagonalized density matrix would look like this, where it's a sum over, again, a set of classical probabilities, but this time it's a density matrix, so it's the outer product of a set of states, and then this is the linear superposition of these outer products. In that case, then C reduces to B. Okay, so that's kind of the observation that you made, but that doesn't necessarily have to be the case. You could look at some other operator instead of the density matrix. You could look at a non-diagonalized version of the density matrix, but generally speaking, that's the connection from C to B. And then last but not least, if rho, the density matrix, if the probabilities in that are, of course, of a special form, say they're proportional to that Boltzmann factor, then C reproduces A. Okay? So kind of got these different levels of entropy all over the place, and but we can connect them. Another technical way that you can connect B and C to A is to say that, so for example, in the canonical ensemble, we seek to maximize the entropy for a system held at some fixed average energy. And so that's actually part of this connecting process. You have to add in that maximization of the entropy condition. But anyway, that's to actually reproduce these equations. Okay, so now some very important observations. So one might ask the following question: if I can connect, for example, C to A, then one might wonder if you can turn this around and say, okay, well, since the world is fundamentally quantum mechanical, is there any sense in which we can say that ordinary thermodynamic entropy, so the thing we encounter when we use the laws of thermodynamics, shouldn't that always basically be equivalent in some way, shape, or form to the von Neumann entropy of the actual full quantum mechanical description of the system? And the answer is no.
Oh.
Did you think it was going to be yes?
I was kind of checking it.
Well, no. Let me explain why. Let me explain why it's not, and then derive or motivate a very, very important inequality that we'll use later on. And the reason is the following. So remember where thermodynamic entropy arises? Where does thermodynamic entropy arise?
Microstates?
Well, you're trying to rely on the statistical definition, which is part of our understanding of it. But generically, thermodynamic entropy arises because we're trying to describe something with a very small number of parameters, which we know really and truthfully has a lot more information in it. So we might just try and describe a box of gas in terms of its temperature, its pressure, its volume, entropy, average energy, whatever. And really and truthfully, we know that there's a gazillion things going on in there, and that set of variables is hardly enough to fully specify the system. So I'm going to introduce a term associated with that, which is the notion of coarse graining. Okay? We're using a very coarse description of the system, and I think I utilized this last time, and I'm going to rely on this again today. So thermodynamic entropy arises because we've coarse grained a system. Okay? Now the von Neumann entropy, if I'm looking at, for example, a diagonalized density matrix, the von Neumann entropy, in principle, is something that you can write down utilizing a complete basis in the Hilbert space of states for your theory. Okay, so for those of you who haven't taken quantum mechanics, if you want to talk about like what is the state of a particle, then you have this vector space, and a vector in that vector space is a description of the state of the particle. So usually it's important to talk about the basis vectors in a vector space. And so for example, if you want to talk about momentum, you have a momentum vector space, and the axes are the different values of the momentum. And an arbitrary momentum state in quantum mechanics can be some superposition or a vector in that space. So you can talk about sort of the most complete description of a quantum mechanical system and construct the associated density matrix. And of course, we know that the complete quantum mechanical description of a system is itself intrinsically limited because of the non-commutativity of operators. So for example, you can't have simultaneous position and momentum eigenspaces. But what I'm saying now is let's just pick the most complete description we can, which is pick a complete set of compatible observables. Okay, and if you've taken quantum mechanics, you know what that means. If you haven't, and you will, you'll find out what that means. So you pick as many things as you can that commute. You look at the basis associated to the eigenstates of all those operators, and then you say, I'm going to construct the most complete and detailed density matrix in terms of that basis. This is a particularly simple thing. This is just an energy basis, but we could add more refinements to the basis. And here's the important observation. There's no coarse graining that you're doing here. Okay, you're being complete. It's just you're handed this quantum mechanical density matrix. You're forced into an ensemble. It's not because you have chosen to describe your system with a very coarse set of parameters. Okay? Now, we can take the fully specified density matrix and then coarse grain it. We can say, I don't want to use all of this refined information, I just want to use these big chunky variables. And so really what you can think about is you're taking the Hilbert space, which is this complete complicated thing, and you're just breaking it into chunks, and you're saying, I'm kind of in this chunk, I'm kind of in this chunk, and this love chunk, I'm in this chunk, and I'm not using the full refinement of the Hilbert space. So if you do that, you can take the von Neumann entropy and you can increase the total entropy through some sort of coarse graining. Okay? So what we find is that we don't necessarily have a quality, but rather we have an inequality which says that the thermodynamic entropy has always got to be larger than the von Neumann entropy of the underlying system, basically getting a quality if we choose not to coarse grain. That's the best we can do. If we do coarse grain, then we get extra contributions to the entropy over and above what we get from the von Neumann case. Okay? This is a key relationship. Write this down and don't forget about it, because it'll get erased and then we'll need it later. Okay? Okay, so before I move on, and I actually have a remarkably small set of pages today, so I feel like I'll comfortably get through everything. So before I move on, I want to just correct something that I said last time. Partly because I trust Zach, who trusts me, whom he shouldn't trust. Therefore, I shouldn't trust him because he trusted me. So there's a sense of self-distrust that's at the root of all this. But anyway, okay. All right, so I want to just make a slight correction of something I said last time, and then we'll get back to black holes and where this is all supposed to be headed.
Just a beacon of lies when it comes to black holes.
So consider so in the statistical case, consider a probability distribution. In case B, that's the statistical case, for a composite system. With just say 2 variables. So 2 degrees of freedom to tweak. And so my 2 variables might be PA, PB, and then there's going to be some assignment of probabilities for each of those variables. Okay? And an observation we can make is that if this probability distribution factorizes, that is, if P, A, B, AJ, BK just becomes PA, AJ, PB, BK. So literally, if this probability distribution factorizes into these completely disjoint factors, then we can make the statement that the statistical entropy, or in case B, SA plus SB is equal to SAB. Okay? And that's the familiar extensivity of thermodynamic entropy. You take two systems with separate entropies. You consider the combined system. The total entropy of the combined system is the sum of the entropies. However, if the distribution does not factorize, that is, if you cannot write the composite probability distribution as two completely disjoint factors, then generically SA plus SB is larger than or equal to SA union SB. Or I'll just call it SAB. Okay. Now, if you think about it, that's a little weird because, for example, I could consider these being non-zero and that being zero, which kind of defies our sort of classical idea of entropy as an extensive quantity. Okay? But what we essentially have here in this situation is classical entanglement. Okay, we like to throw the word entanglement around and say that's a manifestly quantum mechanical property, but it's not. You can have classical entanglement. I mean, this whole notion of probability distributions can be relevant for classical context, and the simple statement that something doesn't factorize, that doesn't require quantum mechanical context. Okay? So, you know, what's a sort of a concrete definition of classical entanglement? Well, I like to think of a bag of hands, right? If I take Zach and cut off his hands, put each hand in a bag and then send those bags to the opposite ends of the universe, if you open up one bag and look in it and see a left hand, you instantly know that the bag on the other end of the universe has a right hand in it. Sounds a lot like the whole Bell. That sounds a whole lot like the setup leading to the EPR paradox, right? But there's no quantum mechanics. Like, maybe Zach would wish there was quantum mechanics and he could tunnel back to a state before his hands were chopped off. I'm going to feel really bad if at some point in the future you end up with an accident. So, but anyway.
That's a correlation.
Yeah. We have to test this now.
Well, so classical
Can we
entanglement.
cut off his hands?
That's fine. That's fine.
Okay.
That's fine. That's fine. So I'm trying to use notions which are going to connect directly to the notions of entropy that I'm going to talk about in the quantum context. Okay. So what statement is true? Go ahead, Jeff.
I'm struggling to, would these be two like separate systems or two systems in the same place?
Location doesn't have anything to do with this.
One example that we worked with in quantum was two coins connected by a spring, right? You flip this one, and you know the probability of ending up with heads over here and tails over here may not just be 50-50 or whatever.
Yeah.
Like there's some correlation between, and this is what Kowalski was saying, is that you have a correlation between the two. The outcome of one more or less determines the outcome of the other.
But I mean, Joe, you're saying you can have like an entropy of a gas and an entropy of a different gas, and you mix them all together. And
Yeah, I'm basically looking at a mixing entropy, but I'm not sure if that's remotely useful here
Not sure yet.
as a
I'm not
concept.
sure.
Yeah.
So let me give you an inequality that is useful in distinguishing the classical from the quantum case. Because last time we used a condition like this to try and define the relationship for the entropies associated with quantum subsystems of a composite system. What we can write down, though, is that for system B, so this is a true statistical entropy context. If we take the entropy of a subsystem, or of a composite system, then that quantity is necessarily larger than the maximum of either SA or SB. Okay, so if I take the composite system AB and break it up into two subsystems A and B, and I compute the separate entropies of the subsystems, the entropy of the total system is larger than the largest of the two of these. Okay? However, this is not true for C. Okay? Because exactly of this example that we talked about last time, where I can take AB to be a pure state, but if A is entangled with B, SA equals SB is not zero, and clearly this inequality is violated. Okay? It doesn't have to be violated in a quantum system, because you don't have to have entanglement between A and B. Okay? But if you do have entanglement between A and B, then generically you're going to violate that. Okay? So in Zach's thesis defense, and probably in many senior design posters to be presented at some point in the near future, we made statements about how thermodynamic entropies have this nice property that if you take a total system with entropy 0 and then you consider a subsystem, the entropy here also has to be 0. Okay? It is true for thermodynamic systems, okay? But it's not necessarily true from just a generic probabilistic entropy context.
But didn't you just write down that it does have to be true? Right? I mean, SA and SB both have to be positive quantities, right? So
Oh, no, I'm sorry,
has to
you're
be
totally
greater than or
right,
equal
you're
to
totally
the
right.
max of SA.
You're totally right. You're right. So saying this is fine. It's the motivation for saying this as coming from some statement like this that is wrong. Okay, so this doesn't follow from the extensivity. Good point. Okay, so these facts are not going to play too much into the black hole story, so I just wanted to kind of be a little bit more honest than I was last time in talking about some of these. These are, like I mentioned last time, these are incredible, notoriously subtle concepts, and they're replete with pitfalls, so you have to be careful. All right, so we're heading back to black holes.
There's a question.
Oh yeah, sorry. All right.
In the case of C that you had there, don't you replace
The von Neumann.
Don't you replace it with an inequality that says that SAB has to be greater than or equal to the difference, and the magnitude of the difference of the two entropes? So wouldn't you be able to create a system in that case where you have an SA and SB, but then SAB could be 0?
So S. Something like that?
Yeah, magnitude.
The magnitude. You're asking me, or you've seen this?
I think I've seen that as the triangle.
That triangle inequality might not be vastly different than the expression that I wrote.
Okay.
If I think about it, I might be able to take that and beat it into that SAB is larger than the maximum of the two. But yeah, so they're probably equivalent, although right off the top of my head, I'm not sure. They seem to convey the same thing though. So, all right. So back to black holes for a bit. So I've now drawn this twice, and I'm going to draw it thrice, and then I'm never going to draw it again. But remember our black hole information paradox, black hole mass M information. We dump the information into the black hole. It increases the size of the black hole by some amount. This is okay since the information is behind the horizon. But then, according to Hawking, the black hole radiates. Eventually there's no horizon, and the radiation is purely thermal. So the spectrum of the radiation coming out depends only on the temperature T at the, which is related to the mass of the black hole at the time that that particular radiation is emitted. But nonetheless, there's simply no way that a thermal radiation profile is going to be able to encode a cow if you throw a cow in. Okay? So, and then we talked a little bit about Hawking's approach to resolve this. We talked a little bit about the fact that this seems to imply non-unitary evolution, so information is lost, which contradicts quantum mechanics. And we talked about how the ADS-CFT correspondence seems to come along and say, well, actually, since gravitational systems can be described at least in some type of context by quantum field theories, which are unitary, then there has to be some information preservation. But what I want to do now is go back and dig a little bit more into this and make the paradox a little more acute. And the first thing we can say is that this story itself is not really that convincing. Yeah.
How is it known that a black hole will evaporate in this way?
What do you mean?
So, like, nobody's ever seen a black hole evaporate. Like, what, like, how do they derive the fact that the black hole will evaporate in this way?
So were you here for the first of these black hole information? Oh, okay. So that was right after Hawking died, and we talked about his derivation of Hawking radiation.
Yeah.
So the derivation of Hawking radiation, that was a whole lecture, so I don't have time to do the whole thing. But here's the key thing, and it's important for what I'm about to say. The key thing about Hawking's derivation is, so here's a black hole. That's the singularity. This is the horizon. For a very large black hole, and astrophysical black holes are very large, the region here around the horizon is not a strongly curved region. You don't have like really radically huge curvatures. You get diverging curvatures as you approach the singularity. A lot of times when we want to kind of quantify curvature, we talk about the tidal effects on a person. So the reason you die when you get to the singularity is that you're dead before you get there, because well before you get there, the gravity on your feet is so different than the gravity on your head that you're stretched and you're dead. But what's key is when you pass through the horizon of a black hole, the tidal effects might be barely noticeable. And in fact, by making the black hole larger and larger and larger, you can reduce the curvature at the horizon to the degree where it's negligible. Okay? And that's important because if you're near the singularity and you have large curvature, if you're doing any kind of quantum anything, you need to be doing quantum gravity. But out here near the horizon, you don't necessarily need to pull in the full toolkit of quantum gravity, which we're not even sure exactly what that is. So what Hawking did was he did quantum field theory in a curved geometry where he was looking at the specifics right around the horizon. And again, it's mildly curved. And so his calculation was utilizing tools which were very well accepted. And then he discovered that, you know, these black holes are irradiating with a thermal distribution. And that's a purely quantum mechanical effect. You don't see that in classical general relativity. But nonetheless, his result is that if there's a black hole, it's radiating. So the consequence is if the black hole is isolated, there's nothing being accreted in, eventually it'll radiate away. Okay? But that begs an important question. Are we sure that it radiates away? So for example, does radiation continue to R goes to 0? Because if you think about it, as the black hole gets smaller and smaller, eventually that horizon is approaching the singularity, And so there's a question of, does Hawking's calculation actually apply once the horizon has gotten small enough? Okay? And the answer is we don't really know. Because you have to pull in full quantum gravity in order to do this calculation. Okay? So, so that's one issue. That actually leads to an out to the yeah, Joe.
Real quick, I know that there's a base mass that a bunch of material has to have to create a black hole.
To collapse, but once you
does
have a
there have to be one
singularity,
to maintain.
once you have a singularity, no, because once you have a singularity, it's not about the total mass there, it's about the density. And after it's collapsed to a point, it's a point. I mean, a point that's a gram is as singular as a point which is a kilogram. The critical density is if you want something to collapse under its own gravitational force. Okay, because you've got to be able to overcome all the other forces. But once you've collapsed to a point, you've already done that.
And there are no repulsive forces available at that point.
We don't really know how to describe the physics of a singularity.
Yeah, that's
If I did, maybe I could give you a more concrete answer, but we don't, and I certainly can't.
You probably wouldn't be here.
That's fair.
If you want to do, a proposal for experimental investigation of this question, in the name of
Let's just make a
science,
black hole. Have fun.
actually it'd be more like la. This is redshift the way it's Anyway, okay. So this actually opens an out to the information paradox, at least in the classical form, and that is, it's possible that there could be some kind of Planck scale remnant. So the black hole evaporates until you get down to a horizon that's about the quantum gravity scale, the Planck scale. Okay, and at that point, the radiation procedure stops, and you're left with this supermassive thing, which is not a black hole, it's some weird quantum gravitational relic. But the important thing about it is maybe the information that we supposedly have lost is still just stuck there. Okay? Because remember, all right, wake up. You can't ask questions if you've been sleeping. So remember, the information problem is that you put information into the black hole, once it's completely gone, all you have is this thermal profile, that the details of that information seem to have been lost. If you're left with something, then you could still have the information hiding inside of it.
So what
Okay.
is that something? It's just a super dense type
Well,
thing?
here's the thing, and this is why I'm talking about this today. It turns out not to matter. Because you actually encounter paradoxical problems before this is even an option.
Oh, Jesus.
Okay? And this is why I spent so much time talking about these different notions of entropy. And this is the reprisal of the information paradox that has come up in more recent years. Again, Hawking's original argument here, it's got these kind of outs, but no, what we're going to talk about today is going to make it a considerably more acute problem that people are still trying to figure out how to address. So, okay, so one version of this problem was actually introduced before the sort of more refined version, and the first version is a little bit easier to digest, and that is consider a bucket of bits. So bits are information, okay, and a black hole, and that is otherwise in isolation. So this black hole is sitting there in an empty universe, and therefore, according to Hawking's calculation, it's radiating. Okay? So that black hole is going to have a mass m, and according to Hawking's derivation, it's radiating with a temperature that is determined by the mass of the black hole. The mass also determines the radius of the black hole. All these numbers are tied together. Okay, and of course, this is purely thermal. So, so we've got radiation coming out, and left to its own devices, the black hole would just evaporate and lose mass and get smaller. Maybe we don't know how it ends. But now let's just imagine taking our bucket of bits and throwing bits in. And bits are both information, but they're also energy. You know, I mean, a dog bone has a lot of information in it and energy. Dogs can extract that by eating the bone. And now let's consider throwing in the bits at a rate that exactly balances the rate of Hawking radiation. What happens to the mass of the black hole?
Constant.
It's constant. So if the rate in is equal to the rate out, then the mass is constant. What does this imply about the radius?
Constant.
What about the area?
Constant.
What about the entropy?
It's
increasing.
Well, the Bekenstein-Hawking entropy of a black hole says it's proportional to the area of the black hole. So if the size of my black hole isn't changing, this thermodynamic entropy should not be changing, but we're adding information to the black hole.
So
And
therefore,
we're not getting that information out. Notice this problem never involves the black hole evaporating away.
This is better.
This is better. Well, there's actually a much better version of it than this. First of all, here we have to somehow rely on the direct connection between information and how that gets transformed into the thermodynamic entropy of the black hole. And we're not 100% sure about how that works. In a statistical underpinning of thermodynamic entropy, where we use probability distributions, and then we talk about generating partition functions and so forth, and the whole statistical mechanics story that leads up to thermodynamics, there's a firm, clear story in terms of counting of microstates associated with the given macrostate, et cetera, et cetera. We don't really have that for a black hole. We can't count the microstates of a black hole. They actually have been counted in a few very special scenarios. Strominger and Vafa calculated the microstates for black holes associated with intersections of various d-branes in string theory, and actually got a result which exactly matched the Bekenstein-Hawking entropy of a black hole. But that's supersymmetric, highly special scenarios that by no means can be done for an average garden variety black hole. So we don't really necessarily have a complete understanding of that statistical underpinning. So it might be that something in that breaks down, and the simple idea of adding bits of information and how that should be reflected in the change in entropy of the black hole, maybe that's not quite. Maybe something in that breaks down so that this isn't such an issue.
If you look at that as a system, doesn't that disobey the second law of thermodynamics? Because the entropy of the black hole is constant, and if you're removing all this stuff, you're losing entropy.
But the
If you take away that, it's
No, the Hawking radiation itself is carrying entropy.
Okay, and that conserves it.
Well, and also your system is not closed. Now you're throwing things into.
You
You're throwing
can call
things
your
outside
system
of
whatever
system.
you want.
Well, so if you call your system everything outside of
Right.
the black hole, you're now throwing things outside of your system.
So
it's
the
okay
entropy
by
of the
Well, I was
external
thinking the information you put in the black hole itself.
Well, then all the
But then the-
information is
the
theoretically
information.
inside the black hole. If you're including everything. So then you're never actually losing anything.
If
Are you saying you're drawing your boundaries of the black hole is not in your system?
So I was thinking the information you're adding to in the black hole will have conserved entropy, but then you lose entropy from your the information you're putting in. But I guess if it's radiating out.
What's happening?
So you.
I mean, this
No,
is the same
that is
information paradox. That is the information paradox, right? That's what you're
Like
saying.
you're
Yeah.
throwing stuff in, but the Bekenstein-Hawking
Right.
entropy isn't actually changing. So yeah.
Isn't that the paradox? That's the paradox.
Okay, we can chew on that in a bit. The picture that I want to paint now is a more concise paradox, and it's the actual paradox that people are trying in various ways currently to try and address. So one quick idea, which I don't think I mentioned last time, maybe I did, but it'll be relevant for what I'm about to talk about. It's the notion of a purification. And Zach has certainly talked about this. My senior design students know about this, but this is basically the inverse of what we do with entanglement entropy. So for example, if I start with a pure state, and then I consider the subsystems A and B, then if there's entanglement, then these two things can have non-zero entropy. But one important observation is that if I start with a pure state and I look at a partition into two pieces, then the entropy of each of those pieces is the entanglement entropy with the other, so they have to be the same. A is as entangled with B as B is with A, and both of them can be non-zero. So this is running it from, I have a big system that's pure, and I consider a small system, and it ends up being entangled. And of course, then there's a density matrix here that has a non-zero von Neumann entropy. For the notion of a purification, what I could do is I could say, suppose I give you a system A. Well, I would just switch the lowercase, it's beyond me. With some density matrix which is not pure. Okay, so it's some distribution. Okay, so in particular, SA is not zero, right? So I literally am just giving you a system, and I'm saying this is not pure. It's you know there's some set of classical probabilities, and the density matrix is a sum, you know. You could ask, well, is there a way that I could take the system you gave me, combine it with another system such that the composite of those two is pure? And it turns out, yes, you can always do that. All right? The only requirement is that the second system has to have at least the same size Hilbert space as the system you're starting out with. And if you do that, if you take a second system B and combine it with A such that the total system is pure, so I'm running this now backwards, then the system AB is called the purification of A. Okay? So there's a reversibility to this argument, and that observation is going to be very important for our sort of final description of the information paradox. So here we go. So let us now consider, and I have been struggling with getting this thing right, and this morning I was fighting with it, and I decided to do what I always do when I can't figure something out.
Figure it out in class.
I went and ran. And I ran, and if you don't exercise, man, exercise is great for figuring out physics. I solve my best problems when I'm out exercising. So I ran, and then I couldn't figure it out, so I ran some more, and I kept on running, and eventually I figured it out. So consider a pure quantum state. Okay, so we've got some pure state that has collapsed into a black hole with mass m. Okay? So remember, m determines, and this is something you learn when you do a little bit of general relativity. The mass determines the Schwarzschild radius, which also determines the area of the horizon. So just one parameter tells you a lot. Okay, so the fact that we have a black hole, forces us to coarse graining. Why does it force us to coarse graining?
You have one parameter?
Because the only thing you can know about a black hole is its mass, its charge, and its angular momentum. That's it. So ignoring charge and angular momentum, literally m is the only number. Okay? So because we have a black hole, i.e. a horizon, that's the important feature of a black hole, we are forced into coarse graining, and so we're going to have some black hole entropy, which is the Bekenstein-Hawking entropy. And it turns out that that's proportional to A. But of course, A is determined by M, so I'm just going to call this proportionality M and just work in terms of M. So equals is proportional. I've set all relevant constants to unity.
Including number 4.
Of course. Okay, there. All right. Screw you guys. I'm going to call them the units of God.
This is why you don't trust yourself.
Okay. So everybody understand that observation?
Yeah, sure.
Okay. Okay. Since we collapsed a pure state, what is the von Neumann entropy of the black hole?
0.
It's 0. It's a pure state. Now remember, this satisfies the necessary condition that the thermal entropy is larger than or equal to the von Neumann entropy, so nothing weird right now. Now, as usual, let it shine. Okay? If we let the black hole radiate, as it loses energy, we find that the black hole, or the Bekenstein-Hawking entropy, which is proportional to, which is equal to the mass, well, as it radiates, it loses mass, so this is heading towards 0 if we let it radiate completely away, just hypothetically, okay? However, now let's consider the von Neumann entropy of the radiation which has come out of the black hole. So I will call that radiation E. So we have the black hole here. It's been radiating for some amount of time, so there's some radiation that's come out of it. And that is, I'm going to refer to as E. And then I is everything that's left in the black hole. Okay? So if we consider the von Neumann entropy of the radiation that has come out of the black hole, clearly this starts at
0.
0, right. Before you've radiated anything, there's no von Neumann entropy because there's no radiation. But then if the black hole completely radiated away, then in principle all of its entropy should be caught up in the radiation that's left the black hole. So in principle this should grow to M. Okay? Now so far we're writing two results that kind of make us feel good about the fact that the total entropy of the universe doesn't change. The entropy the black hole loses is just captured by the outgoing radiation. Okay? Now, oh, no, sorry. I said this and I totally didn't mean that. Radiation. Okay, sorry, the entropy in the emitted radiation starts at 0, and then as you keep emitting, eventually the entire black hole is the radiation that come out. Okay, so the entropy of the black hole should be captured by that emitted radiation. Now I'm going to make an important observation, and this is the thing that was so hard to pick up from the papers that I was reading about this. The radiation that's emitted is not hidden behind a horizon. It's outside of the black hole.
Agreed.
So there's no reason to coarse grain. It's not hidden behind a horizon. So we can go and make measurements of it. Okay? So that means that the entropy of the radiation outside the black hole should be the von Neumann entropy. No horizon, no coarse graining. So this should be the von Neumann entropy. Okay? So what we've said now that I wrote, and now I'm going to write it again, is that the von Neumann entropy of the external radiation should start at 0 and then go to M. Okay? However, this is the von Neumann entropy of the external radiation, but we started with a pure state.
Yeah.
So how should this entropy relate to the von Neumann entropy, the von Neumann entropy of the stuff inside the black hole. It should be the same.
So it should be 0?
Okay, because what's inside and what's outside the black hole together form a pure state with total von Neumann entropy 0, and I'm just looking at subsystems. So their von Neumann entropies can be non-zero, but they have to be the same. Okay? And now to see the paradox, all we have to do is remember that observation that I made at the beginning of the lecture, and I said was going to be very important. S thermo is always greater than or equal to the von Neumann entropy. So what we find is that if we plot entropy versus time, the thermodynamic entropy of the black hole follows a curve that looks like this, starting at m and going to 0. According to this statement and this observation, the entropy, the von Neumann entropy of what's inside the black hole should do this. But that contradicts that inequality. So what should happen is that somehow the von Neumann entropy of what's inside the black hole can grow, but at a certain point, it can't get any larger, and that is exactly when half of the black hole has radiated away. So to see this paradox, you don't even have to go anywhere near total evaporation. All you have to do is think about the situation after half of the black hole is gone. Okay? So what should really be happening to be consistent with this inequality is that the von Neumann entropy of the internal matter should rise and then fall to 0. Okay? But explaining why that happens, how that happens, is still an open area of investigation. And next time we meet, we'll talk about some of the approaches to actually explain that result. Now, just to kind of put this into perspective, because we're talking about black holes, there's nothing intuitive about it. You can take a piece of coal and repeat this story. So a piece of coal, you light it on fire, because that's what we do with coal. It burns, radiation comes out, and after a while the coal is gone, and all you have is the collection of radiation that came out. Okay?
And so,
The entropy, say it again?
and all of the atoms and everything that made it up.
Well, right, no, but the point is that in this context, if you want to talk about the entropy, you never have to coarse grain, because there's no horizon that's forcing you to do that. So you could literally take the coal to be in a pure state, its entropy will rise if you consider the entropy of what's left in conjunction with what's radiated away, and it will follow the entropy of the piece of coal that's left as it burns. It will rise and then fall and eventually hit to 0, and so you can collect all of the stuff that eventually radiated from the coal, and in principle, you could reconstruct all the information about the piece of coal that burned. The difference between this and a black hole is you have to start here with a black hole. And it's because there's a horizon. And the no-hair theorems that arise from that.
So if it follows that curve, does that mean the universal, the energy isn't, or entropy isn't conserved?
So that's the thing. This is not the entropy of the entire system. It's the entropy of a subsystem.
It's all good.
And that does not have to be conserved.
Sure.
So this is entanglement entropy in a quantum system. It can rise and it can fall. The total entropy of this. I mean, that's the weird thing. Like, we always think of, you make the system bigger, then you can accommodate a lot more. But in quantum entanglement entropy, you make the system bigger, everything can be 0.
Yeah.
Even though the internal bits are changing and not canceling. It's not like one's positive and one's negative, they're both positive. So the sort of math of enlarging the system really radically changes when you're dealing with this entanglement entropy. Okay, and just to put a name on this, because I think it's important, this curve is called the page curve. This is called the page time, and that does not have anything to do with the pages of a book, but it's a guy named Don Page, who was a relativist, still around. And the interesting factoid about Don Page, I believe, he's one of the only like really successful physicists who's a devout Christian. And having him do like black holes and cosmology and then reconcile that with his faith, I think is would be a very interesting conversation to have with him. And I think there's some articles written up to that effect if you want to go and pursue Don Page. So anyway, when we do get to schedule another Physics X, I'm going to talk about some approaches to actually addressing this modern form of the contradiction. Okay? Joe.
Does the presence of information affect whether a system is pure or not?
No.
Okay.
No. So no. So it depends on what you mean by the presence of information.
Well,
The saying a state is pure versus saying a state is mixed is a piece of information. But that doesn't have anything to do with coarse graining. We like to think of information in thermodynamics and the statistical underpinnings as being tied to coarse graining, saying if we're only going to describe it in terms of E, V, N, and T, there's a lot of information about what's truly going on that we don't know. So there's a lot of hidden information in coarse graining. The quantum part of this, where you're saying is it a pure state, is it a mixed state, that has nothing to do with coarse graining. It doesn't mean that there's not a relevant
Measure of information.
Yeah, there's a relevant measure of information.
I'm just trying to,
Matt, will you turn the camera off?
Yeah.
if the presence of information would change